Welcome to our one of our last few videos on the nuclear physics unit. This time we're going to be looking at Feynman diagrams, but that is a little bit deceiving because I'm going to talk a little bit about one of our last two learning objectives, or two of our last three learning objectives. So this is going to be part one of a series, so that's going to cover why quarks cannot exist on their own, and this is due to an idea that we call quark confinement. And we're also going to outline the necessity for the Higgs boson and describe its discovery. So I asked you guys to watch a video last time, so we'll just quickly review that and what it looks like, and maybe how you guys might be expected to explain this on an actual test. Okay, so without further ado, part one, let's talk about quarks and why they can't exist on their own. So down here I have a proton, and so as you know, quarks have to exist either in pairs or they have to exist in triplets. That's not how you spell triplets. Oops, triplets. Okay, so they have to exist in hadrons. And what's going on here is imagine for a moment that we are going to exert some energy to pull, let's say, this up quark away from our proton. And so we have to exert a certain amount of energy. Now, as we exert more and more energy, so suppose, quick little review, the strong nuclear force, let's say, for intents and purposes, because it has a value of 1 in terms of the strength of it, it is the strongest force that exists. So when we exert energy, let's say we exert 0.2% of that strong nuclear force energy. So we're starting to pull it a little bit further and further away. And so we might have something that looks, we'll do something like this. Okay, so we have up, down, and then so the up is being pulled a little bit further away. Okay, so suppose we exert more energy. So now suppose, let's say we exert 80% of the strong nuclear force energy. So we're going to pull this quark further and further. So I'm just going to erase that. So our quark is going to be pulled further and further away from its origin point right there. And so we're starting to exert huge amounts of energy that is approaching our strong nuclear force. So now, suppose now that we could exert all the energy to completely separate this up quark. So we would have to exert, at the very minimum, at least an equal amount, which means we're exerting the same full 100% energy as strong nuclear force. Now, the interesting thing about this is the following thing. When we exert the same amount of energy as the strong nuclear force, there is a massive buildup of energy. And what happens, if you, again, think back about one of the fundamental equations, E equals mc squared. So energy can be converted into mass. So suppose we could actually exert that much energy to separate a quark. There is an equivalent amount of energy that will produce additional particles. And so the energy that you exert, for example, may also create additional quarks. So energy will convert itself into matter. And so now what may happen is we could have the up quark here will sort of glue itself back to form the proton. And then now we have an antiparticle forming with the up quark that you just separated. Okay? So now what we've actually done is, because we've exerted so much energy, we've created new quarks, new particles, and that's the idea of confinement, is that in order to overcome that strong nuclear force, the amount of energy that we're generating would be enough to generate new particles. And so that's the idea of confinement. Okay, so just a quick little note here is that the amount of energy necessary to separate a quark will create new matter. Okay, and so there's this idea of that nature just won't allow that single quark to be on its own, right? So how do we know it creates exactly an up quark and an anti-up quark? It's just a study of how nature sort of works in that sense, okay? All right, next up, outline the necessity for the Higgs boson and describe its discovery. Okay, so let's talk a little bit about the Higgs. So both of these guys, this idea of matter being created is really, really interesting. Higgs boson. Okay, so the Higgs boson comes from this idea that there's something called a Higgs field. Sort of like how there is a gravitational field that you cannot see that affects how we live on Earth. The Higgs field, though, is suspected to be everywhere. Okay, so it's literally within the entire fabric of space. So for a moment, though, let's maybe confine this idea to really understand it. So suppose there are a bunch of Pokemon players here. Okay, so Pokemon players love to talk about Pokemon, or they could be a bunch of swimmers talking about swimming. It could be a bunch of physicists talking about physics. Or it could be a bunch of volleyball players talking about volleyball, okay? So imagine we have a room full of Pokemon players. Now, suppose that there is there's two particles that are going to enter this room. Let's say there's two people that are going to enter this room, okay? One of them is like the super Pokemon player. It's Ash, if you are familiar with the series. So let's say Ash Ketchum comes into the room, and he's like the Pokemon star. And so everybody in the room will be like, oh my God, it's Ash Ketchum. I got to talk to him, right? And so what happens then is that people closest to the door that Ash Ketchum enters will start to crowd around him. Okay, and they'll be like, oh, can I get a selfie with you? And so as he moves through the room, more and more people, so let's say this is Ash Ketchum in pink here. So as he moves through the room, more and more people will be drawn towards him. Okay, so that's exactly what we're actually looking at here, is that a quark will interact through the Higgs boson particle, and the more it interacts with the Higgs field, the larger or the greater the amount of mass it will generate. Okay, so when somebody really, really popular, the superstar Pokemon player enters the room, all these people are going to crowd around him, okay? But they can't all crowd around him at the same time because there are some physical limitations, right? For example, this guy over here can maybe see him, take a photo, but he can't get close enough to get a selfie. So he's interacting, but not completely, okay? Whereas other people in the room may not even know, because of all the other people who are blocking, they don't know what's going on, okay? Now, suppose there is So over here, let's say in blue here, let's say we have Michael Phelps, famous, very famous, probably one of the most decorated Olympians. I think it's, hope I don't spell his name wrong, Michael Phelps. And so, multiple time Olympic medal winner. He enters a room, but Michael Phelps doesn't play Pokemon, okay? So these Pokemon players, maybe they're not too interested in swimming. And so when Michael Phelps enters, they're like, that doesn't really matter to me, okay? So Michael Phelps could potentially walk through the entire room and not have anybody pay any attention to him because this is a room full of Pokemon players, not a room full of swimmers. So when a person doesn't interact with the Higgs field, they exert, or they don't create any mass because nobody is drawn to that person. Okay, so you can certainly adapt this for any other leisure activity, whether it's books, movies, sports, and anything else out there. Okay, so that's the Higgs boson field and how the Higgs boson particle works in interacting with the field. Okay, guys, thank you for watching. We'll be back in part 2 with Feynman diagrams.